Last time we proved this corollary. For a field extension of a base field f in E, the set A of elements of E that are algebraic over F constitutes the largest algebraic extension of F in E. And the corollary, the last corollary we proved, which is this one, states that it has no proper algebraic extensions itself inside the field E. So that's where we will continue from. And so it's natural to call such extensions something. We call them totally transcendental, namely extensions where all elements in the difference of the two fields, the base field and the over field, are all transcendental. Applying the discussion to the field of algebraic numbers, we obtain the following. So A is the largest algebraic extension of the field of rational numbers inside the field of complex numbers, and its degree is infinite. This answers the question we asked in the previous video. Why is this infinite? Because for arbitrary natural numbers n and an arbitrary prime p, this polynomial is irreducible, making it, by Eisenstein's criterion and the fact that it is monic, the generator of all polynomials over Q that have square root of nth square root of p as their root. So this field extension is therefore equal to n. Since n was arbitrary, this proves this field extension is infinite degree, although it is algebraic. Going back to finite degree extensions, if this is one such, then by consecutively adjoining elements in the difference between each step, the field that you obtain each step, and E, you exhaust the degree of E. I mean, you start from F, adjoin alpha 1 to it, and then you have F alpha 1, which has smaller degree, which admits a smaller degree with E, and then you adjoin another element alpha 2, which is closer to E in terms of degree, and so on and so forth, until you exhaust the degree of E over F. So you can simply write E as an extension of F by finitely many elements. Now the question, a natural question, is when is a finite dimensional field extension a simple one? Namely one that is obtained by adjoining a single element to the base field. The answer comes from Emil Artin, who proved that a finite dimensional extension is simple precisely when there are finitely many intermediate fields. To prove this theorem, first we need a preliminary result that says if any finite subgroup of the multiplicative group of non-zero elements of a field has to be cyclic. Why is that? Well, if G is such a group, then it is a finite abelian group. And the fundamental theorem of abelian groups, finitely generated or finite abelian groups in particular, says this: in the decomposition of G into P primary cyclic groups, the same P, the same prime, shouldn't appear twice in that list. That is to say, or that's equivalent to saying, that for each prime dividing the order of G, G has only one subgroup of order P. That's the one contained in that P primary component. So let P be a divisor of the order of G, and this means there's an element alpha of order P in G, but then all roots of the polynomial x to the P minus 1 are here. So there's no room for any further roots, for more roots. That proves the statement. Okay, going back to the theorem, which was this. A finite dimensional extension is simple if and only if there are finitely many intermediate fields. First, let's assume that E is a simple extension, say that of f by alpha, or some alpha. In order to prove that there are finitely many intermediate fields, here's what we observe. For each intermediate field K, A is a simple extension, the simple extension of K by alpha, right? So the minimum polynomial of alpha over K is a divisor of that of alpha over F. Now the idea is to associate K with something, with one of these things that we have seen here. It's actually this, right? We have this in mind, the minimum polynomial of alpha over K. Why is that? Because Ex, this polynomial ring, is a unique factorization domain, which means there are only finitely many monic divisors of the polynomial of min f alpha, and min k alpha is one of them. So that's where we start first. That's a good starting point. Now, okay, once we set that function like so, then we need to prove that this function is one-to-one. Obviously, we've just mentioned this is a finite set. So in order to prove that this is finite too, we have to establish that this map phi is 1-1. To do that, well, here's what we do. We associate K with the set C of the coefficients of the minimum polynomial O of alpha over K in a unique way. How do we do that? We will actually prove that K is equal to the extension of F by C. Now it's certainly a subfield of K, right? And it contains the minimum polynomial of alpha over K as well, which proves that the minimum polynomial of Fc of alpha over Fc divides it. But then, because of this containment or inclusion, we have this divisibility relation too, which makes them equal. Okay. Now notice this equality. E is a simple extension of both fields K, or either field K, or Fc. It can be viewed as an extension of a simple extension of either field like that. So we have this degree relationship by theorem, and notice that these degrees are equal to the respective degrees of the minimum polynomials, which we proved to be equal. That implies that this last one, namely the degree of K over Fc, is equal to 1, which means what? Which means K is equal to Fc as desired. That proves the one-to-oneness of the map phi. In other words, the number of intermediate fields between F and E is finite as well. Now let us prove the converse. Let's assume this extension is a simple one. Oh no, let's assume there are finitely many intermediate fields, and we claim that the extension is simple. We'll do induction on the degree of E over F, and jumping right to the step of the inductive step of proving, or assuming this and proving this statement. Let's choose an element alpha in the difference. The inductive assumption tells us that E is a simple extension of this field that I've just put in parentheses. So the inductive hypothesis yields that E is something in this form. Okay, now there are two paths from this point on. First one starts with the assumption that F is infinite. If F is an infinite field, then so is this set. It's an infinite set. Remember that our assumption, we are working under the assumption that there are finitely many intermediate fields between F and E. So the intermediate fields formed by a junction of these elements to F yields a finite set. So this is such intermediate fields as these are just finitely many, which proves by the infinitude assumption on F that there are two, we can find two distinct TIs for which these extension fields are the same. Now, if you study this situation a little bit, this immediately implies that both alpha and beta belong to this field, which proves that this field is equal to this extension, which in turn is equal to E. Okay? That takes care of the first situation when F is an infinite set. If F is finite, then we will resort to the auxiliary result that we just proved before the theorem. If that is finite, then the dimension of E over F being finite implies that E is a finite field too. So this is true. So the subgroup of the multiplicative subgroup of non-zero elements in E is finite as well. Therefore, it has to be cyclic, which means it is generated by some alpha in E. But then it is easy to see that E is the extension of F by alpha. And that proves the theorem and concludes the video. Thank you for listening.